Okay, lesson 11, page 128, number 40. 95 kilogram person is in an elevator. The elevator is accelerating upward. And the question is, what is the apparent weight of the person? So, if we draw a free body diagram of that person, what are the two forces acting on that person? The weight force. So the weight force is acting down, Fg, and what are the forces acting on the person? The bathroom scale underneath is pushing up, yes? And really the normal force should be drawn like over here, because it's like the force underneath pushing up on the person's feet. However, normally it's drawn up here.
In this case, the normal force is greater than the weight force, right?
Exactly. In this case, the normal force is going to be greater than the weight force. Now, keep in mind, when you step on a bathroom scale, what does the bathroom scale actually read? It actually reads what the normal force is. It actually reads how much the bottom of your feet and the scale are being squeezed together. So basically, your apparent weight is always indicated by the bathroom scale, which is always equal to the normal force. Now, normally, if an elevator is not accelerating up or down, how does the normal force compare to the weight force? They're equal. So when you step on the bathroom scale, it reads your normal force, which is usually equal to your weight force. That's why it just thinks. But when you're in an accelerating elevator, the bathroom scale is not going to read your true weight. It's going to read the normal force, and that's why it's called your apparent weight. So really and truly, what we need to find here, we need to find the normal force. Because once we find the normal force, that's what the apparent weight is. Okay? So, we know that the net force equals the mass times the acceleration. If you have a weight force down and a normal force up, and it's accelerating upward, we know the normal force is bigger. What's going to be an expression for the net force in terms of the normal force and the weight force?
Normal force minus weight force.
Exactly. And what's another expression for the weight force? mg. So now we have enough information to solve. It's a 95 kilogram person times 9.81 meters per second squared, or you can use 10 meters per second squared, equals 95 kilograms times, what was the acceleration? 1.8. And if you solve for the normal force, that's what the apparent weight is. You would look down at the bathroom scale and say, oh my God, apparently I weigh, that much.
It's negative.
It shouldn't be negative.
That's I got 11. Well, I'm using that's why. 1103. Yeah.
All right. But they were using 3 sig figs. So it's actually 1.10 times 10 to the 3rd newtons. 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 1.10 times 10 to the 3rd Not on the AP. Sometimes on the regions. Oh, we're taking the regions, and it's just good science. It's just good practice. Okay, so part B, they say it's moving upward with a constant speed. If it's moving upward with a constant speed, as soon as you see those words constant speed, that's your like chain reaction of thoughts. What's the acceleration? 0. And if the acceleration is 0, what's the overall net force? 0 newtons. And if the overall net force is 0, like from F equals ma, then how does the normal force up compare to the weight force down? They're equal to each other. And a lot of people have a hard time with that because how could they be equal if the person's moving with a constant velocity? You know, they weren't equal while the person was accelerating, but once the person gets up to speed, then they're equal. So basically, the normal force is just going to be the weight of the person, which is 95 kilograms times 9.81 meters per second squared, and basically whatever that is, that's what your normal force is, and that's also what your apparent weight is. So in that case, your apparent weight and your and your true weight would be the same. That's why, like in most of the elevator ride, you just feel like yourself. Only at the very beginning, while you're accelerating, and the very end, when you're decelerating, do you feel like a difference in weight. You feel it in your stomach. And then the last part, accelerating downward with an acceleration of 1.3 meters per second squared. Did you have a question, Dave?
Yeah, for part B, when you said acceleration in Fn equals 0, how do you know directly Fn equals Fg? Like, what do you plug into the formula to make it equal?
Well,
like, can I just see the derivation?
You know the net force is equal to the mass times the acceleration. But the acceleration is 0. So it's going to be 95 kilograms times 0 meters per second squared. And what's the expression for the net force still? Either way, depending on your reference frame. So basically Fn minus Fg equals 0. So Fn equals Fg. Okay? And then in the last case, you have your weight force and your normal force, but the person's accelerating downward. So if the person's accelerating downward, there's two ways of going about doing it. You can keep the same reference frame as before. I, myself, personally, I would change the reference frame. I would make down now to be the positive direction. And I would say, look, the overall net force equals the mass times the acceleration. But now that it's accelerating downward, which force is going to be bigger, Fg or Fn? So if I'm making down the positive motion, what's going to be the expression for the net force? Exactly. And that's going to equal m times a. And this over here is going to be 95 kilograms times 9.81 meters per second squared minus Fn equals 95 kilograms times the acceleration. And they say it's downward acceleration of 1.3 meters per second squared. But since I have down as the positive direction, it's just going to be, positive. And then you solve for Fn. And again, that's your apparent weight. So you'd be, oh my goodness, apparently I weigh 808 newtons instead of 950 or whatever for before. That's your apparent weight. Now, other students like to have consistency. So they would have done that last part, keeping up, still being positive, yes? But they would have had, the normal force and the weight force, and they would have said the net force equals the mass times acceleration. But if they're using up as positive, their expression for the net force would still be Fn minus Fg, and then this would be 95 kilograms. But what would they put in for the acceleration? Yes. No. For the actual acceleration. Negative 1.30 meters per second squared. Negative. Because Tom said 1.30 meters per second squared downward. So that would be negative. And if you plug in here, you still get the same answer.